Hi there and welcome back to the College Physics series. In today's lesson, we're going to be focusing on motion on a ramp. This concept shows us how objects move when gravity acts at an angle. We'll explore a special formula for calculating the acceleration for objects that are on an incline and solve problems involving inclines. Be sure to download the guided notes in the description so that way you can follow along with the lesson. Thank you for being here. Let's get started. In our previous lessons, we learned how to break vectors into components and how to use coordinate systems to solve motion problems. Today, we're going to apply that knowledge to a specific scenario, motion on a ramp, or otherwise called motion involving the inclined plane. Objects don't just move horizontally or vertically. When they move along an inclined surface, like a ramp, gravity acts at an angle, no longer just straight down. So therefore, we need to adjust our approach. Let's explore how we analyze motion on a ramp, starting with constant velocity, and then moving on to accelerated motion. Let's begin with our first example. It reads, a skateboarder is rolling up a ramp at 12 meters per second, and the ramp is angled at 15 degrees. How much vertical height does the skateboarder gain after rolling for 5 seconds? We can solve this by breaking the velocity vector into its x and y components. The vertical component will tell us how much height the skateboarder gains. Using trigonometry, we'll calculate the vertical component of the velocity. But first, let's analyze this scenario a little bit more closely by drawing a picture. So in this case, we have the surface drawn here in yellow, and it's angled at 15 degrees. We have a skateboarder who's going to be starting from the bottom, and the skateboarder is going to be rolling up the ramp. We know that the velocity from the beginning all the way to the end is consistent, and it's a constant 12 meters per second. In the beginning, we have this person at the initial horizontal position. Also at the initial vertical position, we know that the object is moving with a constant velocity of 12 meters per second. Over here, this is where we're going to have our final horizontal position, matches up here. We're going to have our final vertical position, which would likely be here, and our velocity is going to remain constant. Notice how I did not tilt my axes like the way we mentioned in the previous video. Because I have not tilted my axes, I'm going to have initial and final positions in both the x and y direction. Later in this video, we'll talk about how we can avoid having this complication. Next, I'm going to draw my knowns and unknowns. I know that my initial horizontal position is 0 meters, as well as my initial vertical position. I know that this time interval is 5 seconds long. I know that my total velocity is 12 meters per second. And I know that this ramp is angled at 15 degrees. What I'm really searching for is how much vertical height. I'm looking for my final vertical position here. The main idea here is that the vertical motion of the skateboarder is determined by the vertical component of the velocity. Analyzing this velocity vector a little bit closer, remember in the last video we said that any vector has a horizontal and vertical component. So here we can draw out, this would be the horizontal one and this one would be the vertical one, Vy and Vx. The horizontal component is what's causing the skateboarder to move left and right. It's what's changing its horizontal position. The vertical component is what will be changing the vertical position of the skateboarder. And that is the component that we are interested in. I know that my angle here is 15 degrees. The Vy is opposite to my angle measure, and my hypotenuse is always the longest side. Using SOHCAHTOA, given my opposite and hypotenuse, as well as my angle measure, I'm going to be using the sine. Or you can remember the shortcut that we talked about in the previous video. It's just going to be V sine theta. The magnitude of the velocity is 12 meters per second. And the angle is 15 degrees. Therefore, my vertical component of the velocity is going to be 3.1 meters per second. Now I know the rate at which the vertical position of the skateboarder is changing by. So notice if we look back, let's identify a key word here. This refers to constant velocity. Because this is an example involving constant velocity, the only equation that applies in this scenario is the equation of uniform motion. I know that my initial vertical position is 0. Therefore, my final vertical position is just going to be my vertical component of the velocity multiplied by the time interval. Therefore, this is going to be 3.1 meters per second multiplied by 5 seconds. Therefore, the final vertical position will be 15.5 meters. And this completes this example involving constant velocity motion on a ramp. Next, let's explore a different type of motion, accelerated motion on a ramp. There's one major idea that we're going to talk about before we jump into examples. And let's see what kind of scenario we are looking at here. In our case, we just have some sort of ramp, and we have an object such as a box that's placed on top. And what happens is that the object is going to move down the ramp. Here's our first key idea. This first key idea is that any object sliding down a frictionless ramp accelerates due to the action of gravity, but it is constrained to accelerate parallel to the surface. Let's explore this type of motion in more detail. I'm going to have my object, again, the box. I just mentioned that the reason why any object will slide down a ramp is because of the acceleration due to gravity. There's only one direction in which the acceleration due to gravity points, and that's downward. So I'm going to draw an arrow here, and we're going to draw a vector downwards. And this is going to represent the acceleration due to free fall. What I'm also going to do is that I'm going to set up my coordinate axes to be aligned with the ramp. What that means is that here, in the same direction of the ramp, is going to be my x-axis. Parallel to it will be my y-axis. This is going to make it easier for me to solve problems. And if that doesn't really make sense to you, here's what I'm doing. I'm taking a regular xy axis, and what I'm doing is that I'm placing it over, and I am rotating it so that it is aligned with my ramp. It looks a little bit more complicated now, but that is essentially what's happening. So that'll be my y-axis, that'll be my x-axis down here. So I know that this ramp is tilted at some angle, but now there's something interesting that happens to my acceleration due to free fall vector. Before, when we studied just normal, the typical xy coordinate plane, up and down vectors had only one component, and that was y. The ax was 0, and the ay was just equal to the magnitude of a. But in this case, now our axes are tilted. Therefore, we have both an x and a y component. My x component is going to point parallel to the surface. This is going to be my ax. It points in the direction of the x-axis. My y component is going to complete the triangle here and is going to be parallel to the y-axis. Due to geometry, the angle that the ramp is tilted at is exactly the angle in this position right here. So let me draw that on the outside. This is my acceleration due to free fall. In my tilted version, I have an x component right here, and I have a y component pointing this way. The angle measure is in that part where my 90 degree is right there. That is what is going on when an object is accelerating down a ramp. So what is the acceleration of an object as it falls down a ramp? Well, we can go ahead and figure that out. The object only accelerates in the direction of ax. That's what I'm going to be interested in. Well, opposite the 90 degrees is always the hypotenuse. Opposite of the angle measure, that's just opposite. O and h gives me a sine. So the sine of theta is going to be equal to my opposite over my hypotenuse. In this case, my opposite is going to be ax and my hypotenuse is going to be a. In this case, it's a due to free fall. To get x, I'm going to multiply by the acceleration due to free fall on both sides. What I'm going to find is that the acceleration for an object going down the ramp is the acceleration due to free fall multiplied by the sine of theta. If you remember what the acceleration due to free fall is, its magnitude is just g. And the direction of the acceleration will depend on what you define to be positive and what you define to be the negative direction. So in the end, the acceleration is going to be plus or minus g sine theta. And that will be the acceleration for any object moving along a ramp. So now, whenever we have an object that is sliding down the ramp, the magnitude of the acceleration will always be g sine theta. You will have to assign the positive or the negative depending on your scenario. With that said, let's move into the next example. So the question reads, a car starts from rest and accelerates down a 500-meter track with a vertical drop of 100 meters. What is the car's final speed at the end of the race? Well, I can draw out the scenario to help me understand what's going on. So I know we are going down a 500-meter track. So that could maybe look like this. But at the same time we're going down this track, we end up moving downwards by 100 meters. That means that my track must be diagonal. So this is going to be 500 meters and this drop is 100 meters. This means I can represent the scenario as a right triangle with an angle measure in that corner above the horizontal. So I have a car up here. Now I need to consider my directions. What I'm going to do is that I'm going to call my x-axis in the same direction of this ramp, where positive is going down and my negative is going the other way. So if you want to picture this, it's going to look like this. I'm going to take my normal XY axis. I'm going to put my origin at the starting point of this object. Then what's going to happen is that I'm going to tilt my axis so that the horizontal is in line with the motion. So my positive x-axis is going to be going down the ramp. The negative is going to be going backwards. And of course, up and down is where they belong. So my car is going to start at the origin and is going to fall all the way down this 100-meter drop on the surface that is 500 meters long. So at the beginning, I'm going to get my initial horizontal position, my initial horizontal velocity, and my initial time. At the very end, I'm going to find my final position, my final velocity, and the final time. Notice when I'm labeling my variables here, it's all x direction because that's what I called this direction to be. I chose for this direction of motion to be in the positive x direction. If I hadn't, then I would have different initial and final horizontal positions as well as vertical positions, and it would be difficult to describe my horizontal and vertical velocities initially and at the end. So tilting our axis in this scenario simplifies everything, and my life becomes easier because of that. Next, let's establish our knowns and unknowns. I know that this car begins at 0, because I decide that that is what the starting point is. It finishes 500 meters down. I know that its initial velocity is 0 because it started at rest, and I do not know what this final velocity is. So I'm missing something here. I know that the object is accelerating down the ramp, but it doesn't tell me what the acceleration is. I can use what we just established. Remember that we said that any object that is sliding down a ramp is going to have an acceleration of g sine theta. So let's go ahead and figure out what that is. Notice how I'm calling this positive acceleration because the object is moving in the positive direction. So the velocity and the acceleration all point in the same direction. So therefore, this object speeds up. Okay, so I know what g is, that's 9.8, but I don't know what my angle is. Luckily, I know from this corner, 100 is my opposite. Opposite of the 90 degrees is my hypotenuse. Opposite and hypotenuse, that gives me the sine once again. So the sine of the angle is just going to be 100 opposite over hypotenuse, 500. And this is going to reduce down to 1/5, 1 over 5. Remember the steps that we talked about in a previous video. In order for me to get the angle measure, I'm going to switch the positions of the 1/5 and the angle. And at the same time, I'm going to call this the inverse sine. So altogether, the inverse sine of 1/5, that's going to be equal to my angle measure. The calculator is going to tell me that it is 11.5 degrees. Now that I know that angle measure, I can figure out what my acceleration is. This is 9.8 meters per second squared times the sine of 11.5. Therefore, my acceleration is going to be 2 meters per second squared. Now that I know what my acceleration is, I can figure out what my final velocity at the end is. So to figure that out, I'm going to use this equation. Luckily for us, our initial velocity is 0 because this car starts from rest. Now to solve for my final velocity, I need to take the square root. And I'm interested in a positive velocity only, so I don't need to consider any negative roots. So all that I have to do is multiply 2 times the acceleration, 2 meters per second squared, multiplied by my displacement. Well, my displacement is just final minus initial. It looks like my final is 500 minus 0. I'm going to get 500 meters and take the square root of that. So finally, my calculator is going to tell me 44.7 meters per second. And that will complete this example of accelerated motion down a ramp. Really briefly, I want to talk about limiting cases. Limiting cases refer to situations where a system's behavior or solution is examined under extreme conditions or parameters. For our scenario of the inclined plane, our highest possible angle measure is 90 degrees and our lowest is 0 degrees. So what we want to do is see what happens when we plug in those types of angle measures and compare them to what we expect. If my angle is 0 degrees, that means I'm completely flat. So I should not expect acceleration from an object that's 0 degrees. I should expect acceleration from an object that is greater than 0 degrees. And the highest possible case is 90 degrees. So if this is my surface and then my ramp has suddenly turned vertical like this would be an angle measure of 90 degrees. What happens if I were to place a box right there? Well, it wouldn't really touch the surface. It would just fall. So let's see what happens when we test each case out. So when theta is equal to 0 degrees, what happens to my acceleration? Well, I get plus or minus g sine theta. And when I plug in 0 for theta, the sine of 0 is 0. That matches exactly what I expect. How about case number 2, when my angle measures 90 degrees? My acceleration is plus or minus g sine theta, but now I'm going to plug in 90 for the angle. The sine of 90 is just equal to 1, so therefore I get plus or minus g. That exactly makes sense. If my ramp is at 90 degrees, it is completely vertical. Let's think this through. Right now, if you take a look at your bed, it's flat horizontal and you're falling asleep there on your pillow. Now, how about you rotate your bed so that it is standing up? So try laying on your bed when it's vertical. You're going to fall right down. You're going to fall right off the bed. It's like trying to sleep on a wall. It's completely vertical and you're going to be in free fall if you try to jump up and lay on the wall. That's exactly what we expect for an object whose ramp has an angle measure of 90 degrees. The object just ends up in free fall. So this was just a quick detour and checking our limiting cases. Now let's do one last example. Our next example reads, a car speeds up to climb a hill. The car reaches a speed of 30 meters per second at the bottom of the hill, which has a 15-degree incline. It takes 3 seconds to climb the hill. How fast is the car going at the top? Let's go ahead and draw out this scenario. So this would be the flat surface at the bottom. Our hill is actually 15 degrees. Our car is going to start from the bottom and it's going to reach the top. Now I'm going to draw out my Cartesian coordinates, but I'm going to align them with the hill, just like that. So I'm going to call this direction the positive x direction. This would be the negative x direction. So by setting up my coordinate system like this, I'm defining the motion of the car to be positive. Notice that in this example, it doesn't say it travels at a constant speed. The question actually implies that there is a difference or that there is a change in this car's velocity, because at the very bottom it's traveling 30 and the question is asking me how fast is the car going at the top. Well, if you think about it, I have acceleration fighting the car, pulling it downward. It's almost as if I rolled a ball up a hill, it's going to eventually slow down and then it's going to roll back downwards. That's kind of what's happening with this car. So let's establish our important symbols. So because I've labeled this x direction to be in the direction of the car's motion, I have my initial horizontal position at the beginning, my initial velocity, and my initial time. At the end here, so I have my final horizontal position, my final horizontal velocity, and my final time. Let's go ahead and establish some knowns and unknowns. I know that initially the car is going to begin at 0 because I defined the beginning to be 0. The hill is angled at a 15-degree angle measure. At the beginning of the motion, the car is traveling at 30 meters per second. I know that it takes 3 seconds for this car to reach the top of the hill. And I'm being asked, what is a final velocity? Well, there's one item that can change an object's velocity, and that is acceleration. At the current moment, I do not know what this acceleration is. But here's what I know about this problem. This problem can be categorized as motion on a ramp. For objects that are moving on a ramp, the acceleration will be plus or minus g sine theta. Well, which is it, plus or minus? Well, the acceleration is pointing towards the left of the x-axis. Therefore, my acceleration is going to be negative. To complete this, I'm going to get negative 9.8 meters per second squared multiplied by the sine of 15. I'm going to get my acceleration to be negative 2.5 meters per second squared. Now, I'm going to use my acceleration with one of the kinematic formulas to figure out what my final velocity is. So putting my knowns and unknowns together, I'm going to use this formula to find what the final velocity is. Luckily for me, this is already solved for, so all I have to do is plug in the numbers. My initial velocity is 30 meters per second. I'm adding my acceleration, but my acceleration is negative, so it's going to be minus 2.5 meters per second squared multiplied by this time interval of 3 seconds. So I'm going to get 30 minus 7.5 and that's going to give me 22.5 meters per second. That is going to be the final velocity at which this car is traveling at the top of the hill. Here is another problem for you to try. The try it yourself problem reads, a box slides down a ramp at a 45-degree angle from rest. Calculate the acceleration of the box along the incline, how fast the box is moving after 4 seconds, and the distance the box has traveled in those 4 seconds. That wraps up our lesson on motion on a ramp. Today we learned how to calculate the vertical height gained during constant velocity motion and how to calculate the final speed when climbing a hill or moving down a slope with acceleration. If you found this lesson helpful, please consider liking the video, subscribing to the channel, and sharing it with others. Don't forget to leave your answer to the try it yourself problem in the comments. I'd love to see how you did. Thank you for being a part of the College Physics series. I look forward to seeing you in the next lesson.